Okay, well we'll get started, and so today I'm going to cover just maybe some conceptual topics regarding hypothesis testing. Okay, and then on Friday I'll pass out the T table and we'll take a look at the T distribution. Okay, so here we're going to cover conceptual topics with hypothesis testing. Okay, so keep in mind, we make conclusions. When it comes to conclusions, what are the two conclusions we can make in a hypothesis test?
You either reject it or not.
Yeah, when it comes to conclusions, we can decide either to reject the null hypothesis or not to reject the null hypothesis. When do we decide to reject the null hypothesis? We do this when the p-value is less than alpha, and we do not do this. We do not reject the null, so we do not reject the null when the p-value is greater than alpha, okay? All right, and so in the ideal scenarios, ideally, what happens? Okay, if the null hypothesis is true in reality, what is the conclusion we will make? If the null hypothesis is true in reality, we hope that our conclusion is, what do we want our conclusion to be? Is not to reject the null, right? Okay. If the null hypothesis is true, we hope our conclusion is not to reject it. Yeah, question?
Fail to reject and not to reject.
Yeah, fail to reject, not to reject, those are the same things. Yeah. And on the other hand, if the null hypothesis is false in reality, okay? So if the truth is that the null hypothesis is false, we hope our conclusion will be to reject the null hypothesis. Okay, so if the statement asserted in the null hypothesis is true, so for example, let's say the null hypothesis says that the bucket of M&Ms has 17% green. Okay, and if that's actually true, we hope our conclusion will be we have no evidence to say that the bucket is not 17% green, so we don't reject that. On the other hand, if the truth is the bucket is 17% green, but our null hypothesis says, I think the bucket is 25% green. Okay, well, we hope that when we do our hypothesis test, at the end of the test, we say, I have reason to believe that the bucket is not 25% green, but is something else. And that would be the correct conclusion to make because the bucket is actually 17% green. That's what we want in the ideal scenario. Okay? However, there are errors that are inherent to the process of hypothesis testing. Okay? There are two types of errors. that are, unavoidable in the process of hypothesis testing. Okay? These errors are not a result of us making a mistake, but it's a result of the fact that we are trying to make a conclusion based on limited data. Okay? When you don't have all of the data, there's a chance that you're going to make a mistake. Okay? And when statistics was being developed as a field, the statisticians recognized that there are two types of errors, and they didn't have good names for them, so they called them type 1 and type 2 error. Type 1 error and type 2 error. Later on, we came up with better names for these things, but the original names have stuck around, okay? So the two types of errors are type 1 error, okay? The better name for type 1 error is the false positive. And we have the type 2 error. Okay, and that would be the false negative. All right, so let me describe what the false positive is, okay? So the type 1 error. Okay, this is the false positive. And what it means is that in reality, the null hypothesis is true. Okay? However, we make the conclusion, which is wrong. We make the conclusion to reject the null hypothesis. That's a type 1 error. The null hypothesis is true, meaning it should not be rejected, but we make the conclusion to reject the null hypothesis. Okay? That's the definition there. So, so I should say, the error is not because we did our math wrong. Okay, the error is not because we made a mistake in calculations. Instead, what this means is that because of random sampling, we happened to just get a weird sample that led us to the wrong conclusion. Okay? So what happens? What causes type 1 error is that because of random sampling, we happened to get a weird sample that leads us to the wrong conclusion. Okay, so example. Okay, I have a bucket. The bucket is 17% green. Okay, this is the truth. The truth is that the bucket is 17% green. Our null hypothesis is that P is equal to 17%. So the null hypothesis is correct. The null hypothesis is true. However, we get a random sample. Maybe we get a random sample where P hat is 0.24, okay? Just because of random chance. I get P hat equal to 0.24. The calculations give a p-value of 0.03, okay? So we reject the null hypothesis, but that was the wrong decision, okay? We follow, I mean, that's the right thing to do in that scenario. However, rejecting the null hypothesis is wrong because in truth, the bucket really is 17% green, okay? So we reject the null hypothesis, and that is the wrong conclusion. Okay. Does that make sense? That's the type 1 error. Means your conclusion is to reject the null hypothesis. But the truth of the matter is that the null hypothesis is true. So you're not supposed to reject it. But because of random sampling, maybe we make the wrong conclusion. And that's a risk that we just run. Okay, so that's the false positive. Did you guys get that all down? Okay. All right, let's talk about the false negative. The type 2 error. The false negative. Okay, so in truth, the null hypothesis is false. Okay, in truth, the null hypothesis is false, but our conclusion is do not reject the null hypothesis, or fail to reject the null hypothesis. That's the false negative. Okay, again, it's not because we did something wrong, but it's just because of random sampling, maybe we didn't get a p-value low enough. So an example of this scenario, okay, so the bucket is 17% green, okay? So the bucket is 17% green. The null hypothesis will state, maybe the null hypothesis says that P is equal to 25%. Okay, so maybe that's what the null hypothesis states. So this is wrong, right? This is not true. The null hypothesis is false. Okay, that's what we have going on here. But you know, because of random sampling, with random sampling, okay, when it's 17% green, you know, maybe we get a sample where p hat is equal to, I don't know, 21%. That could happen, right? The bucket's 17%. Because of random sampling, we get 21%, okay? When we look at 21% versus the null hypothesis of 25%, it turns out that, you know, when we do our calculations, you know, I'm just making up these numbers here. I'm just doing an example here. When we do our calculations, maybe we get, we end up with the p-value equal to, I don't know, 13%. Okay? Based on this p-value, we do not reject the null hypothesis. So we say, you know, how different is 21% from 25%? Well, the p-value for that is 13%, right? Based on our calculations, right, we compare 0.21 versus 0.25. Okay, we end up with a p-value of 13%. So based on the p-value, we do not reject the null hypothesis, and we say we do not have evidence that the proportion is different from 25%. Okay? But that conclusion is wrong, because in reality, the bucket is only 17% green. Okay? Is wrong. The bucket is 17% green. Okay? But we didn't come to that conclusion. That's a type 2 error. That's the false negative. We did not reject the null, but the null is false and should have been rejected. Okay, type 1 error and type 2 error. Conceptually, are these okay? All right. Okay, so earlier we said our significance level alpha determines when we reject or not reject, right? Determines whether we reject or do not reject the null hypothesis. Okay? Our choice of alpha actually reflects our willingness to make a type 1 error. Okay, so if alpha, so what we have is that alpha, our significance level, is actually equal to the probability of making a type 1 error. Okay, so if alpha is 5%, okay, we will make type 1 error 5% of the time. Okay, and you might be thinking, well, I don't want to make type 1 error. Why don't I just make a small alpha? If alpha is the risk of making type 1 error, why don't I just pick alpha to be 1%? So now I only have a 1% chance of type 1 error. Or why don't I choose alpha to be 0? So I have a 0% chance of making type 1 error. Okay? Well, what happens is that if we lower our alpha, we increase the risk of making a type 2 error. Okay? If we reduce alpha, okay? Reducing alpha means we will reject the null hypothesis less often, right? Because we reject the null when the p-value is smaller than alpha. So if that alpha is really, really small, then that p-value will not reach that threshold to reject the null. So we're going to be rejecting the null less often, which inherently increases our risk of type 2 error. Okay, so if we reduce alpha, we increase the risk of type 2 error. Okay, and so the symbol we use for type 2 error is beta. Beta is the probability of a type 2 error. Okay. Alpha looks like the letter A and is the first letter of the Greek alphabet. So type 1 goes with alpha. Beta looks like a B. It's the second letter of the Greek alphabet. So type 2 goes with beta. So alpha for 1, beta for 2. That's actually where we get the word alphabet from. Alpha and beta just stuck together for our letters. So we have, if we reduce alpha, we increase the risk of type 2 error. Beta is the probability of a type 2 error. So there's a balance, okay? We can choose, we get to choose alpha. Okay? We do not get to directly choose beta. but our choice of alpha does affect beta. All right, so let me kind of give you an example where, you know, whether we want to pick a big alpha or a small alpha depends on the context of the situation, on whether we would rather make type 1 or type 2 error, and you know which error is worse in what scenario here. Okay. I'll let you guys catch up on writing all this down. Okay. So let's think of a criminal trial. Okay. So in the United States, we always say that the defendant is presumed innocent until proven guilty, right? So one of these, that we have the null and the alternative hypothesis. One will be the defendant is innocent and the other will be defendant is guilty. Which one should be the null hypothesis? Innocent, okay? The null hypothesis will be defendant is innocent, and the alternative will be defendant is guilty. Okay? And we presume innocence, okay, or we presume the null hypothesis to be true until there's enough data or evidence to convince us otherwise. So we start off there, okay? And the in the ideal scenario, or here, well, let's, before we talk about the ideal scenario, what are the conclusions that the judge or jury can make? That jury / judge can make. Okay? The jury can say, what can the jury say? The jury can say guilty, and that is equivalent to rejecting or not rejecting the null hypothesis. Yeah, this would be rejecting the null. And then the jury, what else can the jury say? The jury can say not guilty. And that is equivalent to not reject the null, right? Or fail to reject the null. Notice the jury never says innocent. Okay? The jury never says innocent, and likewise, we never say accept the null. Okay? Because saying not guilty is not the same thing as saying innocent. It just means there was not enough evidence to convince us that of guilty. Okay. All right. Okay. So in the ideal scenario, the ideal scenarios will be that if the defendant is innocent, what will the jury say? The jury says not guilty, right? That's what we want. If the defendant is innocent, we want the jury to say not guilty. Okay? So, or if the null hypothesis is true, we do not reject the null hypothesis. Okay? And on the other hand, if the defendant is guilty, we want the jury to say, what do we want the jury to say if the defendant is guilty? We want the jury to say guilty. Meaning, or if the null hypothesis is false, we reject the null hypothesis. These are the ideal scenarios. Okay, let's make a clicker question here. Okay, so my clicker question will be, so we'll stick with the criminal trial example. But let me just copy these hypotheses here. Okay, so this is what we have. All right, and so the question is, what is a type 1 error in the context of this problem, okay? So we convict a guilty person. We convict an innocent person. Okay. We acquit. Acquit means you say not guilty. You can acquit a guilty person, or you can acquit an innocent person. Okay, so if you want to talk to your neighbor about which of these answers is the correct one, you can do that. What is a type 1 error? Okay, okay, I'm going to click stop. All right, let's take a look. Okay, and that is correct. Okay, so if we think about what this is, we convict an innocent person. This means the null hypothesis is true. All right, let me have you guys settle down, please. Okay, null hypothesis is true, meaning a defendant is innocent. Okay, but we reject the null hypothesis. Okay, that would be we convict an innocent person. So rejecting the null, is that okay? What would a type 2 error be? C. C would be the type 2 error. Null is false, but we do not reject the null. All right. And, you know, convicting a guilty person, this is the ideal case. And acquitting an innocent person, that's also the ideal case. These are the correct decisions to make in those scenarios. All right, is this okay? All right, in the context, in this context, and this is always up for debate, but which type of error is worse? Is the type 1 error or is the type 2 error worse? Is it worse to convict an innocent person or worse to acquit a guilty person? Okay, well, you know, it is debatable, but you know, we will say the type 1 error is worse than the type 2 error, okay? All right, especially if you think of, you know, I don't know how you guys feel about death penalty cases, but if there's a death penalty case, a type 1 error would be really bad, right? That means you're executing someone who is not guilty of a crime, okay? So the type 1 error is worse than the type 2. Okay, so if this is the scenario, all right, here's your second clicker question. If the type 1 error is worse than the type 2 error, here's the question. Do we want to use a large or a small alpha? Okay, so if you think large alpha is desired, or small alpha desired. Okay, type 1 error is worse than type 2 error. Do we want a large alpha or do we want a small alpha in this scenario? All right, let's take a look at how you guys responded. Okay, and that is that's the case. Small alpha is desired. So recall that alpha is equal to the probability of a type 1 error. Okay, so if the type 1 error is worse, we want to pick a small alpha to reduce our risk of type 1 error. Okay, and they actually say this. If you were to serve on a jury, and they're talking about, you know, when you make the sentence or decision, they don't say use a small alpha in your decision making process, but what do they tell the jury?
Reasonable doubt.
They say beyond a reasonable doubt, right? That's the phrase that they use, because when it comes to convicting someone, they don't want people to convict because they just have a hunch or they have a gut feeling. Okay, they want it to be beyond a reasonable doubt, which is equivalent to saying use a small alpha. Make sure that the evidence is very convincing before you reject the null hypothesis in that case. Okay? However, they don't say only convict if you're 100% absolutely sure, right? Why don't they say 100% sure?
They're never sure.
Yeah, they do not say be 100% sure. Okay? Because that's not possible, right? We don't have all of the data. We cannot travel back in time to the moment when the crime was committed to see who is actually responsible. Okay? So, you know, and we can't read minds. We don't know exactly what's going on. So they do not say be 100% sure because we can never be sure. We can never be 100% sure. All right? Imagine you're a judge, or that there's a judge, and the judge sentences someone and says guilty. Okay? And then it turns out later that this person was not actually guilty. You know, maybe some DNA evidence comes forward, and the person is exonerated from the crime. It turns out that they were actually innocent of the crime, and so the judge maybe has a moral dilemma and says, you know, I feel really bad that I sentenced an innocent person, or I convicted an innocent person, and says I never want to make that mistake again. Okay, I never want to send an innocent person to prison. Okay, what's the only way the judge can be absolutely sure of never making that mistake again?
Making alpha zero.
Yeah, so the only way the judge can be absolutely sure of never mistakenly convicting an innocent person is to never convict anybody. Okay? If the judge says, I want alpha to be 0, I want my type 1 error to be 0, then that means your alpha has to be 0, and the only way you can achieve that is by saying not guilty to every single person who shows up in court. Okay? And if you say not guilty to every single person, then you are no longer a judge. You're just a rubber stamp, and so that's you cannot eliminate type 1 error. Okay, and there might be personal preferences. Probably all judges have a low alpha in their decision making, but some people might have lower or higher levels of alpha than others. But no one can have an alpha of 0. Okay, so the only way to completely avoid type 1 error is to have alpha equal to 0. But if alpha is equal to 0, you will never reject the null hypothesis. Okay? And so if alpha is equal to 0, you will never reject the null hypothesis, or, a judge never convicts anyone. Okay? And that defeats the whole point of hypothesis testing, okay? And then the flip side is also the case. If you want to avoid type 2 error, you can choose a larger alpha, and you say, I want to make sure that I don't acquit anybody who's guilty. Like, I want to make sure that nobody gets away with any kind of crime. This is my town. No one gets away with crime. Then that means everybody who shows up in court is going to be automatically guilty, right? And that's well, that doesn't sound very American. So I'm sure you'd be removed. Maybe that's yeah. Okay. Well. All right. Is that good? Let me give you another scenario where maybe the type 2 error is worse than the type 1. Okay. Okay. So let's say okay. So for some kind of like maybe STD screening or any kind of really disease screening. Okay. So in general, doctors will assume that you are healthy unless you show evidence otherwise. So the null hypothesis will be patient is disease-free. And then the alternative will be patient carries some kind of disease. Okay? And in this scenario, ideally, all healthy people will test negative. Okay? And then all people with the disease will test positive. Okay? So the type 1 error, this is the false positive. This means a healthy person is flagged positive as, we'll say a healthy person tests positive for the disease. Okay, and the type 2 error is the false negative. This would be, you know, a person with the disease tests negative for the disease. Okay. Now, both of these scenarios we want to avoid. A false positive, you know, sucks for the healthy person. But generally, you know, if you test positive once, a lot of times you might be retested just to make sure it wasn't a false positive. But in general, if you test negative, they're not going to say, well, let's just make sure that was a real actual negative. And so, from an epidemiological standpoint, you know, the false negative is a lot more dangerous, because the false negative means someone who actually has a disease thinks that he or she is healthy and may then transmit it to other people. Okay, so type 2 error can have serious epidemiological consequences. Okay, I mean, it doesn't even have to be STD. It could be any disease, right? Ebola or whatever. Okay, we want to make sure that everybody who carries the disease is identified as such. Same thing goes for, you know, cancer screening. Okay, if somebody actually has cancer, we want to detect it early. We don't want to say, we don't ever want to tell someone who actually has cancer, oh, you're fine, you're healthy, you know, come back next year, and that could actually cause the cancer to worsen. Whereas a type 1 error for something like cancer screening, just hang on for a second. Type 1 error, although could be scary, usually you don't say, okay, like, so for example, you know, men are supposed to do a testicular self-exam once a month, women are supposed to do a breast self-exam once a month, and they say, you know, if you detect anything strange, go to the doctor and see about it. They don't say if you detect anything strange, that means automatically you have cancer, and we're going to start you on some drastic treatments, okay? But those types of things, they're working with a larger alpha, because type 2 error is worse. This is why when you go to WebMD and you type in any of your symptoms, a lot of times it says it could be cancer, and that's because you guys laugh, but that's because, you know, from WebMD's standpoint, they don't want to ever give you the sense that, oh, you're fine, you're healthy, and there's no problem, when there actually could be a problem. They'd rather you go to the doctor, get further screening to get an actual conclusion. So anyway, that's type 1 error, type 2 error, and how our tests affect that.